if you could mute on your end, just so the background noise is limited, that'd be great. So I'm going to talk today about the Colorado Plateau. We do a lot of boating. We're lucky people to be able to boat on the Colorado Plateau pretty routinely. It's only about 3 or 4 hours from Denver proper to get to the eastern edge of the Colorado Plateau. And I want to talk about why do the rocks look like they do, and why do we see similar styles of rocks and geography across a really wide area in Western United States. Oops, won't let me, there we go. So we're going to talk about where is the Colorado Plateau, what is it, what is geology, and why do we care? And then we'll do a little bit of a primer on geology so we can talk about more complex topics and what's so special about the Colorado Plateau, and then a little bit of a geologic history of the rocks, and then a special treat for you guys. And I just realized that the text is not as easy to read. The background picture should be muted more, but that's okay. I'll read them for you. So the Colorado Plateau is in 4 states: Utah, Colorado, Arizona, and New Mexico. And it encompasses, let me get my notes here. It encompasses an area of about 135,000 square miles, which is about the size of Norway. The elevations range from about 2,500 feet to about 12,500 feet, so 10,000 feet in elevation range, and is made up mostly of largely flat-lying sedimentary rocks, but it also has some volcanic rocks on the surface, particularly down in Arizona, but also a little bit in New Mexico and Utah, not so much in Colorado. It is a physiographic province of the United States, and if you're ever interested in what a physiographic province is, it's just an area with consistently similar geography and geomorphology of an area. And the United States is broken up by geographers and geologists into a number of physiographic provinces, and that you could Google it and it'll show you. There's like the Appalachian province and the Southern Plains province and all these different areas in the Northern Plains. It has the greatest concentration of US national parks and national monuments outside of the Washington, D.C. metropolitan area. It's amazing. There's 9 national parks, including Grand Canyon, Zion, Bryce Canyon, Capitol Reef, Canyonlands, Arches, Mesa Verde, and the Petrified Forest. And the 18 national monuments include Bear's Ears, Rainbow Bridge, Dinosaur, Hovenweep, Woodpotki, Sunset Crater Volcano, the Grand Staircase Escalante, Natural Bridges, Canyons of the Ancients, the Chaco Culture National Historic Park, and the Colorado National Monument. And not only do we have this many different national parks and national monuments throughout the Colorado Plateau, but each one is really unique in its own way, but still remarkably similar in its geologic history and formation. So it's pretty amazing region. So some of the rivers that we actually boat on in this area include the Yampa, the White, the San Juan. We don't always boat the Little Colorado, but sometimes we'll float it with our life jackets on. The Colorado River, especially, and the Green River in particular. Other ones include the Escalante River, like the Muddy Creek, Dirty Devil River, and some other smaller rivers that all feed into the Colorado River. So here's our first minty question. So I'm going to switch. So we're going to go to, oh my God, I lost my mouse. Crap. Yeah. How do I get out? Here we go. I'm going to screen share. We're going to go to minty.com and go and type in the code 701495.9 all together. And you'll come up with these choices on which rivers have you boated on the Colorado Plateau. And just select all, you can select as many as you want. And then at the bottom, say yes or no to submit. Oops, not done that one. So you'll see as people, so 4 people, if you look in the lower right-hand corner, it tells you how many people have responded. So 5 people have responded, and how many people have done which rivers. And A lot of people have done Desolation Canyon. A lot of people have done Ruby Horse Thief. A lot of people have done other. I'm curious to see what, if you've done other, put it in the chat box. I'm curious to see what those others are. 7 people have responded. I think we have about 7 or 8 people on the call. So nobody's done Cataract. I have not done Cataract, and I haven't done Muddy Creek either, and I really want to do both of those. So 8 people have responded. Cool. So this just kind of gives you an idea of what experience we've had amongst our group about which rivers we've done. And I didn't have Lador in there because Lador technically is not in the Colorado Plateau, just in case you were wondering why that one wasn't there. Go back to the presentation and play. Oh, there we go. So we're going to go now to talk about geology. Why do we care? What is it? Sheldon doesn't think it's a real science, but I disagree. Geology is the study of the earth, and that includes everything from the center of the earth out, the morphology of it, what it's composed of, the history of it, all kind of different things. So geology has a number of different types of like sub categories or sub disciplines, including plate tectonics, paleontology, geomorphology. That picture is on Mars, those Barken dunes. It's pretty phenomenal. The structural geology, stratigraphy, and hydrology. And paleontology is actually one that you don't really realize how important it is to the study of earth science until you get into the depths. But paleontology is the way we've done relative dating of rock units throughout the world, because in many cases, when you're looking at sedimentary rocks, you can't do radiometric dating directly on sedimentary rocks because those rocks are composed of fragments of other rocks, so if you did the dating, you'd be dating the original rock that broke down to make the sedimentary rocks. So what they look at is these a lot of times microfossils, and they figure out which microfossils are older than other ones. They can do a relative age dating. And then when they get these happy circumstances where you have like an igneous rock crossing a sedimentary rock, you know, the igneous rock is younger than the sedimentary rock, so you can at least bracket the ages of some of these paleontological, these microfossils, and you can get relative age datings with a little bit pinning down of the actual radiometric dates. So it's pretty amazing how paleontology really fits in. You'd think it was kind of an obscure science that, you know, you only look at just because you like dinosaurs, but it's actually quite important in the overall study of geology as a whole. So we're gonna go even more basic though. What is a rock and what is a mineral? Oh, the mineral didn't show up. Well, that one on the right says, what is a mineral? So a mineral is, hold on a second, let me find my notes here. Mineral is a naturally occurring inorganic crystalline solid. So it has to have a crystal structure, a lattice structure, has to be inorganic, can't be organic, can have carbon, like carbon and oxygen in organic molecules, and it has to be naturally occurring. We can make all kind of rocks in weird ways, but we consider a mineral to be a naturally occurring object. So and a rock is just an aggregate of minerals that are either physically or chemically cemented together. Rocks can also have glass, like volcanic glass in them, when a molten rock cools really fast, but for the most part, their rocks are composed of different aggregates of minerals. And I don't know if you remember this picture on the left with the rock. That was the one where the guy said, did a text online that says, a large rock the size of a small rock is in the road. That's from back in the winter last year over in San Miguel County. So there's 3 different types of rocks. There's igneous, sedimentary, and metamorphic, or classic punk and hard if you don't really follow geology very closely. And so we're going to talk about each one of those. Sedimentary rocks are rocks that are composed of fragments of pre-existing rock, either deceased or deceased organisms like fossils, or chemical precipitants, which is where like you have an inland sea and it precipitates out salt or limestone, calcite, sorry. So there's different types of sedimentary rocks, include sandstone, siltstone, shale, conglomerate, which is large class, limestone and dolomite, which are chemical precipitants or composed of microfossils. And the most important thing about sedimentary rocks to think about is that sedimentary rocks tell us about the environment at the time they were being deposited. They really tell us the story of what was happening at the surface of the earth at the time of that deposition. So the Blacktail Canyon is in the Tapete Sandstone. Tapete Sandstone happens to be a beach sand. So you know that you're on the edge of some sort of a sea. And if you look at broader scale, laterally, several miles or tens of miles, you'll find, you may find a terrestrial rock equivalent age one direction and a submarine rock in the other direction, so you know which way the ocean was at the time that was deposited. This is Blacktail Canyon in the Grand Canyon, and also Matcatamimba Canyon in the Grand Canyon. Both of those are sedimentary rocks, and they're both, the Matcatamimba is actually limestone and Blacktail is sandstone. Pretty fun. The next type of rock is igneous rocks, and igneous rocks are formed from melted rock material that cooled and hardened. And there's two basic types. There's intrusive rocks, which cool under the surface of the earth, where they can cool over a long period of time, and therefore the crystals get very large or relatively large in our inner lock, so you don't have any glass because it had time to cool slowly enough that the crystals could form their lattice. And then the extrusive rock is like basalt, where it actually extrudes over the surface, out on the surface of the earth, like from a volcano or from sort of a fissure. Yeah, basalt is one kind, it's darker. Andesite and rhyolite is typically like a light buff gray color. It often has glass in it if you look at it under a microscope, along with some crystals that were already in the melt before it was erupted. And then you often will also have holes where you have what they call vesicles, where as the rock came out of the ground, the pressure release allowed the gases that were in solution to come out of solution. So it's like when you open a can of Coke and it fizzes. The magma does the same thing. As it comes out, it gets released, and that's why you often have holes in the basalt or in your rhyolite. So that's intrusive and extrusive. And then the last type is metamorphic rock. And metamorphic rock forms from pre-existing rocks of any kind, sedimentary, igneous, or other metamorphic rock that have been changed by heat and pressure. So the one on the bottom has garnets in it, and the one on top is called a phyllite, and it's got a lot of mica. The mica is very oriented because of the stress that was put on the rock at deep depths. But you can think of it like when you bake a cake, when you put the batter in, it looks like one thing and it has a different consistency. When you take the cake out, and once it's been baked, it has a different consistency. It's a different substance. It's not the same substance. It's made of the same atoms and elements maybe, but it's a different substance. And the same thing happens with metamorphic rocks. You're changing some minerals into other minerals as you put it under heat and pressure. And if you're ever really interested, look up metamorphic rocks. Then you can look at metamorphic rocks that form at high pressure, low temperature, or high pressure, high temperature, or low pressure, high temperature. All these different ones make different types of metamorphic rocks. So you look at the mineral assemblage in those rocks to tell what the regime was when that rock was formed. You can tell what the temperature and pressure was. And the metamorphic rock in the Colorado Plateau is all basically basement rock. So it's all the stuff underneath all the sedimentary rocks. Like this is a picture of the Grand Canyon in the black rocks. This is either the Vishnu schist or the Brahma schist. I don't remember which one, but it's one of the schists, and a schist is a type of metamorphic rock that we see. We also see metamorphic rocks in Westwater and in black rocks at Ruby Horse Thief and in Cataract Canyon. And I don't believe we see it in Desolation Canyon, but definitely see it in Lador Canyon before you get into the Colorado Plateau there. So metamorphic rocks basically form kind of the foundation of the basement rock of the whole Colorado Plateau area. So the next thing we're going to talk about is the geologic timescale. Now this is a nice chart. It tells you about, so it's oldest on the bottom right and youngest on the upper left. So you go from Archean, Proterozoic, those are all part of the Precambrian area. Then you have the three different zoics. You have the Paleozoic, the Mesozoic, and the Cenozoic. And it gets younger as you go to the left. But I really like this picture better. So this picture shows you, so if you look at from the top, like from the 12 o'clock position all the way to the 10 p.m. position or 10 a.m. position, that's all Precambrian. That's the vast majority of the history of the Earth is represented in rocks that are basically 540 million years old or older. And if you look at the rocks that that basement rock I talked about that was like in the Grand Canyon and in Westwater Canyon. There's two actually in the Grand Canyon. There's actually two separate rock types. There's the black rocks, Westwater Canyon. There's Zoroaster granite and the schist in Grand Canyon. Those are all about 1.7 billion years old, been dated by radiometric age dating. And then the Grand Canyon supergroup, which we'll talk about in a little bit, is about 650 million years old to 1250 million years old. So I want you to notice though, the difference between the ages of the Grand Canyon supergroup and the Brahma and the Vishnu schists is greater than the difference between the Grand Canyon supergroup and any of the other Phanerozoic, Paleozoic, Mesozoic, and Cenozoic rocks that we see in the rest of the canyon. So it's one of those things where until you see a graph like this, you don't really understand, or you can't visualize, at least I can't visualize, how much time the Precambrian takes of Earth's history. And most of those rocks that we see in the Precambrian area, the Hadean, Archean, and Proterozoic, are metamorphosed, and it can be difficult to tell what the original rock type was before there was metamorphosed, because they can be really, really strongly have been metamorphosed under high heat and high pressure, so they were buried very deeply. And any kind of fossil assemblages or sedimentary structures are not there anymore. So it's really hard to know what the history of the Earth, the surface of the Earth looked like for about 80% of the Earth's history. So it's this kind of gives a perspective of that. And all the remainder of the sedimentary rocks that we'll talk about on the Colorado Plateau are all Cambrian, which is the oldest Paleozoic, to basically the oldest Cenozoic, the light green rocks that we see in that area. So I like this slide a lot. This is a pretty nice way to see how we can tell the age of the rocks. You can also see the blue line that goes around the outside of the circle, the navy blue, so about 2.2 or 2.3 billion years old. That's the oldest living organism fossils that we can find, and those are the eukaryotes. There are prokaryotes that are, we believe, up to 4 billion years old, but I don't know enough about those to know if they're considered to be life or like pseudo-life, kind of like viruses are considered to be pseudo-alive. So I'm not sure about that. Multicellular life didn't happen until halfway through the Proterozoic. So it's pretty amazing. So let's see here. Go to the next slide. So now we're going to talk about some of the disciplines of geology, and these play a part in how we can learn about the history of the Colorado Plateau. So on the left, you see what we call a stratigraphic column, and usually you'll see you'll see the oldest at the bottom and the youngest at the top, and those gaps are called unconformities or disconformities, and we'll talk about those specifically in a little bit, where either the rock wasn't deposited, or it was deposited and eroded, or we don't really know what happened because the rock is not there from that time period. And as you go up the river, up the stratigraphic column, you can tell by some of the symbology on the rock what kind of rocks. Like the brick-looking one is limestone, the dashy one is shales, and the dotted ones typically are sandstones. And also the profile shows like sandstones and limestones tend to be cliff formers, and shales tend to be slope formers. So you can see that a little bit here, where the cliff formers, like the Weber sandstone, is almost a vertical one, whereas the donut shale and the humbug formation have an angle to them. So those are softer, less resistant rocks, and so they form shales. They form slopes, sorry. But stratigraphy is basically the description of classification of sedimentary rocks. So, and we put them in this sedimentary column so that you can kind of see at a glance what you see at a particular location. And you can also use this to talk about the history of what the surface of the Earth looked like over time as each one of these formations were being formed. And then I like this one because you have the Precambrian at the bottom, the Cambrian, Devonian, the special sauce, the Albee patty, the pickles, and the cheese, and then you get up to the Mississippian. So I don't know if you guys have ever been around geologists very much, but we, as Sheldon noted, we're not real scientists, so we don't take ourselves very seriously. So unconformities. So there's unconformities, disconformities. and angular unconformities. And I'm going to catch up with myself in my notes. This is my good friend Bob, and he and I were on the Grand Canyon in 2018, and he's also a geologist, and we were both just thrilled to put our finger right on the great unconformity in the bottom of the Grand Canyon. So this is the difference between, looks like the Zoroaster granite and maybe probably the Vishnu schist, and the contact between those two and the sandstone above it, and the age date. So the difference in age between those rock on that his elbows on and the rock that's behind his head, the Vishnu schist is about 1.7 billion years old, and the I can't think of the name of the rock. The Tapete sandstone is about 540 million years old. So that's over 1.2 billion years of difference in age is represented by that gap. So we're missing, it's like we have the pages of a book of Earth's history, and we're missing a lot of pages of the book at that one spot. And you can actually look at that spot. If you look at that contact carefully, you can actually see that the top of the top of the bottom unit has been weathered, and we call it paleosol. So it had been weathered a little bit. So it was subaerial. It wasn't underwater. It was it was above water, subaerial, and had a soil formation on it before the beach sandstone, the beach sands were laid on it. And then later, as the beach sands became sandstone over time. So the different types of unconformities. You can just say unconformity, that makes perfectly reasonable sense. An unconformity is technically between basically a sedimentary rock and either igneous or metamorphic rock is an unconformity. A disconformity is between two sandstone layers that are parallel. There's no tilting between one layer and the other. So you'll see those gaps with the vertical lines through in the strat column. Those are disconformities. And then angular unconformity is where you have there's also between two sedimentary layers where the bottom rock is at an angle, sedimentary beds are at an angle to the top rock. So there's an angle there. You can see it when you look. You might have to stand back a little bit to see it, but you can see it a little bit. So those are the unconformities, and that's how we know that there was erosion happening there at that time. Structural geology has some, I'll just talk about three main things in structural geology that come into play in the Colorado Plateau, and that is joints, faults, and folds. Joints are just cracks in the rock, and they can be rhythmic or regular and related to tectonic stresses, and that's in the Needles District and the Canyonlands. If you've ever been there, the fins, those are all resulting from joints. They're basically cracks in the rock, but they don't have any movement, so they're not considered faults. But they're joints. And you can see here that the river is controlled by the joint pattern in the rocks in Canyonlands. And then you have faults. This is actually the famous San Andreas fault, which is a right lateral. So if you're standing on one side, it looks like the other side is moving to the right relative to what you're standing on. Doesn't matter which side you're standing on, the other side's always moving to the right. And you can see here where the rivers have been the river courses have been changed by the faults between the North American plate and the Pacific plate. This is an extreme example, of course. On the right, you can see a picture of a fault. This is in, I believe, Escalante National Monument, yeah, Escalante, and where the white material is down thrust on relative to the red rock on the right. And so there's lateral faults, be right lateral or left lateral. And then there's reverse faults where the movement is vertical and one side is pushed up relative to the other. So they call it the hanging wall and the footwall. The footwall is below the fault plane. The hanging wall is above the fault plane. If you have the hanging wall pushed up relative to the footwall, it's a reverse fault because you have compression. It requires compression to do that. And if you have extension, then the footwall will be down dropped relative to the hanging wall will be down dropped relative to the footwall. And so that's what we call a normal fault. So normal faults are extensional, reverse faults are compressional, and lateral faults are basically like lateral movement for whatever reason. Structural geology, this is the last of the folds. This is a strat column versus almost like it's a cross section across a good part of Utah, and it shows the San Rafael swell and the very gentle fold. The vertical axis is dramatically magnified relative to the horizontal axis here. This is probably over about 50 or 60 miles, and the vertical axis is not even, maybe almost 2 miles in length. So you can see it's dramatically exaggerated. But if anybody's been to the San Rafael swell, it's really amazing. And that is part of a fold. Folds often are where a fault will die out. You can see at the bottom of that picture where the Precambrian basement rock, those metamorphic rocks we saw at the bottom of the Grand Canyon and in Westwater, there's a fault there that tends to get reactivated over time. And but as it dies out, it turns into a fold. That's not really unusual. It happens quite a bit. And then now we'll talk about hydrology, because hydrology really is important on the Colorado Plateau. Basically, you have the hydrologic cycle, of course. You have, and then you also have groundwater, saturated zone, unsaturated zone, and also you can have what we call confined aquifers, where you have they can't get, there's like a layer of clay above the water where it can't get out, and you have it'll be under pressure, and you'll have springs coming out of the ground at that point, and a lot of snow. Snowpack is really critical to the water supply in the Colorado River Valley, the whole Colorado River system, which all the way up from Wyoming all the way down to Utah and over to Arizona. Geomorphology is also pretty critical to why the Colorado Plateau is pretty unique. And so you can look at this, the meandering pattern, or the pattern of a stream, if it's meandering versus braided. So meandering is on the left, braided is on the right. And if it's meandering, it'll have more suspended load versus the braided pattern will have more bed load. Bed load is just the material that's kind of forced along the bed of the river versus being basically suspended in the river. The meandering pattern will be finer grained. If you think about the Mississippi River, is finer grained than like a rocky river in a mountain, which is coarser grained. The meandering pattern on the left is more stable than a braided pattern on the right. And most importantly, or most obviously, the meandering pattern streams have a low slope. So the difference between over a mile of how much that river is dropped is going to be much less, typically speaking, in a meandering pattern than it will be in a braided pattern, which would be a high slope. So that's geomorphology. Is also, you talk about terraces, talk about how the underlying geology affects how it erodes and therefore how it looks. So you can see in the picture on the left, the plateaus, some of the rocks are cliff formers, and some of those rocks are slope formers. And the slope formers tend to be shales and rocks that are relatively easily eroded, versus the cliff formers are like limestones and well indurated sandstones, which are much more resistant to erosion. So you can kind of look at that and see what, you can kind of guess at what the rocks are. And so we're talking about the Colorado Plateau. So now that we have had our little geology primer, we're talking about the Colorado Plateau specifically. So here again is the picture of where we are. We're talking about the Colorado, Utah, Arizona, New Mexico, Four Corners area of the Colorado Plateau. And this the Colorado Plateau province, so the Colorado Plateau physiographic province is broken down into smaller, like kind of sub-physiographic provinces, as shown in this picture here, like the high plateaus of Utah, the Grand Canyon province, the Black Canyon of the Gunnison National Park. Oh, I'm sorry, the Uinta Basin, those kind of things. This also shows a lot of the national parks in the area. Let me see if I had something specific I wanted to say there. Nope. Okay. The structural geology. So this is really critical. So why the rock looks the way it do. So the overall, looking west across the Colorado Plateau, so the Grand Canyon's on the left, and you get over to the right, you're looking at things like younger rocks that are such as Zion National Park and those other ones. Colorado National Monument are in the younger rocks. You can see how, yeah, the kind of the maroon at the bottom of the Grand Canyon, that's the basement rocks. Those are the metamorphic rocks. And as you go up, the tan is Cambrian, and then the top of the Kaibab Plateau is the Kaibab Formation, which is at the oldest part of the Cretaceous, the Cenozoic era. So most of the Grand Canyon is Paleozoic. And then if you go from the Kaibab Plateau up to the Pink Cliffs, that is almost all Cenozoic. So through the age of the dinosaurs, so Triassic, Jurassic, and Cretaceous. And as you get to the youngest part of the Tertiary period, then we don't have any rock units left. So either they weren't ever deposited or they've been eroded away. So the oldest rocks we have are about 50 to 60 million years old, the Pink Cliffs, which is the Claron Formation. Again, and so if you look at this is over hundreds, I think 100 miles or 150 miles. There are very, very few faults. And you also notice, with the exception of the Kaibab Plateau, which is kind of a gentle upwarp that's probably fed by those faults in the basement down like where the St. Grand Canyon Supergroup is. That's a very gentle upwarp. You could call it a fold if you wanted to. Most people would call it a warp instead of a fold, until you get way over towards Cedar City, Utah, where you have some significant faulting in the hurricane fault. There's very little structural geology going on in most of the Colorado Plateau. And you can kind of see here the Vermilion Cliffs, the White Cliffs, the Gray Cliffs, and the Pink Cliffs as you go north along the Colorado Plateau. And so if you look down here, so at the bottom of the strat column, there's the Vishnu schist. That's that 1.7 billion year old basement rocks. And then you have the Tepid sandstone up to the red wall, to the Kaibab limestone. So on the right, you can see the bracket. That's the Grand Canyon, the Paleozoic rocks. And then the rest of those units are pretty constant across the entire Colorado Plateau. What that means is that the environment of deposition was very similar across the entirety of the Colorado Plateau. It also shows, if you look at through the Claron Formation, that the environment of deposition across most of, if not all of the Colorado Plateau, and probably areas outside of the Colorado Plateau, was at or near or just below sea level for hundreds of millions of years with very little uplift. There was uplift going on all around the Colorado Plateau. We'll talk about that in a little bit with the history, but the Colorado Plateau itself was very, very stable and received a lot of the material that was coming off those mountains to the west and to the east as they rose up and then got eroded down, and then rose up again and got eroded down. That's where a lot of the material that makes up these sandstones and siltstones and shales came from, was these mountain ranges that were off to the east and west primarily, a little bit to the south of the Colorado Plateau. So, but the plateau itself was right at sea level the entire time. And that's just remarkable. It's one of the things that makes the Colorado Plateau so special, is that the environment of deposition over millions of years was so similar across such a wide area and created some highly variegated colors of rocks over hundreds of millions of years. It's amazing. So here's another thing I want to talk about too. Even though we talk about stratigraphic columns in one spot, this is a stratigraphic column, and you can see at the top it says west, west central, and east. So as you go, the rocks don't only change vertically over time, which is the vertical axis is time, but if you go across laterally across the surface of the earth, they also change. And that's what I was talking about, where you can look at, if one spot is a beach sand, and if you go to the east and that spot is a marine shale, and if you go to the west and that spot is kind of like a low, right at sea level, like swampy terrestrial area where you have meandering rivers coming into the sea through the beach dunes, then you can see spatially over both spatially, east and west, north and south, but also over time how these environments change. And that's how, we always see how they make like the Pangea supercontinent, and they have these great videos about how the continents broke up and came back together. Well, that's how they did it. They looked at these geoscientists took data from all over the world and looked at different correlating microfossils across the earth, so they could correlate the different units time-wise, and then looked at as basalts and other volcanic rocks are laid down, they keep a residual, they capture the magnetic signature of the Earth, so they know which way is north or south as the magnetic poles have switched. But that can give you kind of the orientation of the continent, and then as they come together and go apart, and that's how they did it. It took years of data collection, and then probably even more years of putting all that information together to understand the history of the Earth over time. And it's pretty remarkable. They make those pretty simple, basic videos of how, you know, Gondwanaland came together and then Pangea came together and broke apart. But that information was from years of data collection and compilation from geologists. We're not a real science though. So we're going to go to Minty question number 2. So let me change the screen. So it's the same code number. Don't change your code number. It doesn't matter if you do though, because I can, oops, dang it. I don't have a mouse. There we go. So I can't do it without going back here. So we're going to share this. And I'm going to go to the next screen, I think. There we go. So name some of the disciplines of geology, and you can put in multiple answers. You can put in more than one word. It doesn't matter. But I'm going to put in, for example, I'm going to put in stratigraphy, and then stratigraphy. Oops, can't spell. And then you can submit multiple answers and multiple times. So there we go. That was mine. You can also put in other ones. Paleontology is a big one. Yeah, it's pretty fun. It's I remember being pretty amazed at how crucial paleontology was to learning about the history of the Earth. I hadn't realized that. All right, so five people. Oh, let me put that in there. So yeah, scissors.
Hey, Lynn, I got a question.
Yeah, sure.
A few slides back, the Vishnu schist shows that was where in the Grand Canyon. But then, you know, if you're on like Ruby Horse Thief or Westwater,
yeah,
it's there too. And so why is it there and then also in the Grand Canyon?
It's actually what you see in Westwater and Ruby Horse Thief is actually a different rock. It's a different age. I believe it's more closer to 2 billion years old than the 1.7 that you see in the bottom of the Grand Canyon. But
so it's not the Vishnu schist.
It's not the Vishnu schist. It's a metamorphic, what we call basement rock, which is basically lumping together the metamorphic rock that all the sedimentary rock is sitting on top of. So it's not the same thing.
Is it schist or it's not schist either?
It's it actually in the Westwater, it goes from schist to gneiss and then back to schist. And then there's a phyllite part too. So phyllite is a lower grade. Basically it had a lower temperature and or pressure. And then, so it goes phyllite, schist, and then gneiss. And gneiss is the most, G-N-E-I-S-S. That's the rock that's been under the most pressure and temperature. It's been under such high pressure and temperature that part of it, the rock melted. So that's why you see those big crystals of quartz, kind of the white in there.
And you're describing all the black rock that you see in Westwater or Ruby Horse Thief.
Yep.
Okay.
Yeah.
Thanks.
And there's actually a good geologic summary of Westwater Canyon. If you're ever interested, I can send that over to you.
Oh, yeah.
Yeah, that'd be awesome.
Yeah. Cool. So yeah, just kind of, and the other thing about using Minty, just so you know, if you're doing this for your own presentation, it records how many people reported. It's what they say is anonymous, like who said what is anonymous, but they tell you how many people reported and what the aggregate things they reported are. So most people said paleontology. So probably, I don't know, 5 people said paleontology and 1 person said rock, you know. And then, so the size of this one is related to how many people said it. So yeah. Cool. So we're going to go back to presentation. Here we go. And then play. Cool. Okay. So now we're going to talk about the evolution of the Colorado Plateau, basically the history. So we're going to talk about basically, it's going to be, it's going to be 6 broad periods. So 6, actually, I think it's 7 slides. That we're going to talk about these in pretty basic terms. So the period 1, we always go in geology, you always go oldest to youngest, which I'll talk about that in a little bit later, how I was kind of disappointed in something, but that's okay, I'll survive. So period 1 is basically 2 time periods. This is where we pointed out in that that time, the circular time picture, where you had the crystalline basement was 2.0 to 1.7 billion years old. That's got the Vishnu schist and the Zoroaster granite is in that time period. And then the Grand Canyon supergroup is 1.25 to 0.75 billion years old. So the difference between the youngest supergroup and the Tapete sandstone, which is about 530 million years old, is not that much. It's maybe 200 million years, which in geology speaking isn't that much, compared to the difference in the Grand Canyon supergroup and the crystalline basement itself. So I think I can go back to that slide. Let me see. Go. Yes. Nope. Wrong one. This one. So this is where I was talking about. So the Grand Canyon supergroup is about 1 billion years old, and the Proterozoic rocks are, you know, the Zoroaster granite and Vishnu schist. Those are all 1.7 billion years old. So now I'm going to guess at the right one. Let's see here. Here we go. Great, back. Okay, so this is, we don't have a lot of information about the basement rock, metamorphic rock. From what I've read, the host rock, the original rock that was originally metamorphosed, is probably a shale or shaly sandstone. So probably something, you know, superficial. It wouldn't be something in the water, so it'd be subaerial or maybe shallow seas where you're depositing sand, or maybe river deposits. But we don't really know. Not many sedimentary structures are left in that rock. It's been metamorphosed pretty strongly. In the Grand Canyon supergroup, there is some limestone rocks, and there are some shallow sea rocks. These, so basically we know that it was some kind of an ocean environment or a shallow sea or right at sea level. And then something happened. So these rocks were formed, they were deposited, and then they were turned into rocks. They had to be under some kind of pressure and temperature to make them into rock. Then they were somehow tilted and then eroded off before the Tapete sandstone was deposited about 520 million years old. So in that 200 million year gap between the youngest part of this Grand Canyon supergroup and when the Tapete sandstone beach sands were being laid down, a lot went on to those rocks. They were pretty much tortured, made into rock and then tilted and eroded off, and then the ocean came in and covered them up again with some sand. Pretty interesting. That would be, I'd like to actually look at the Grand Canyon supergroup rocks in more detail and learn about them, because they're all Precambrian rocks, and they may have some Precambrian fossil structures left in them. I don't remember where they are. The next group we're talking about is the up through the Redwall limestone, and this is the story of a sea. So the sea came in from the west. The Tapete sandstone in western Grand Canyon area is older than the Tapete sandstone in the eastern part of the Grand Canyon. So we know that the sea came in very slowly over millions of years. It rose very slowly, and it came in from the west and went to the east and went past the Grand Canyon, because the next unit is called the Bright Angel Shale. And look at remember how I told you about how the profile changes? The Bright Angel Shale is a slope former. It's not very resistant to erosion. So so they show that when they have in the stratigraphic column, the outline, the profile of the stratigraphic column shows that. So the Bright Angel Shale is a shallow marine shale. The Moab limestone is a shallow marine limestone. So the ocean's still there. The ocean stays at that spot for, I forget how old exactly the Moab limestone is. But then after the Moab limestone was deposited, the ocean went out for a little bit because we have a disconformity between the red wall limestone and the Moab limestone. And you can see remnants of what was there in the Temple Butte Formation. That's why it shows up in that little weird way, like almost like a scour, because they found remnants of the Temple Butte. It didn't all get eroded away. So there was something, but the rest of the Temple Butte was there presumably before it got eroded away. And then the ocean came back in and deposited the red wall limestone. And the red wall limestone, if you've ever been to the Grand Canyon, was hundreds of feet thick. I think it's up to 700 feet thick, quite pure limestone, a little bit of dolomite, which means it has a little magnesium in it instead of just calcium. But it also, after that was deposited, also the seas went out again because the Surprise Canyon Formation, remnants of it are left between the red wall limestone and the Supai group. And also the top of the red wall limestone is very karsty. Karst is like when you have caves where the surface water dissolves away the limestones. It's got paleosol. Remember I'm talking about how you can have a soil developing on the surface and it gets kind of preserved. We call it a paleosol. So there's a paleosol at the top of the red wall limestone as well. And then next, so that's basically the sea came in, went out, came in, went out, came back in. The next period is the Permian. So basically the Supai group is Permian aged through the lower Triassic aged rocks. And let's see, look at my notes here. So at this time, to the east of the Uncompahgre, east of the Colorado Plateau, the first of the Uncompahgre uplifts came up in like where Colorado is now. So the first mountains that occur where the Uncompahgre mountains are today, those have been kind of rejuvenated from this same historic mountain chain that was back in the Permian age, which is about 290 million years old. And so this Uncompahgre uplift shed, as it eroded down over millions of years, shed rocks, and those rocks formed the Supai group, the Hermit Formation, the Coconino Sandstone, Toroweep, and the Kaibab formations. And those tend to be clastic rocks, which means they don't have limestone in them. Limestone is a precipitant rock, and like sandstones and shales, they're clastic rocks. And so almost all of the youngest Paleozoic rocks are clastic rocks. And that is what let them know that we have this Uncompahgre uplift to the east. The other thing that let us know about that is that if you go east, like near Westwater, you don't have any of these formations because they were either uplifted and eroded off. The younger, like the Moab limestone and the red wall limestones, they may have actually occurred there, but then during the Uncompahgre uplift, that area is on the very western edge of that area. They were probably uplifted and eroded away. And so they may have turned into some of these other rocks. And the colors, the color of the rocks has a lot to do with how much iron is in them. So they higher iron rocks turn red and lower iron rocks don't turn red, basically. They just retain the color of the original class of the rock. So basically, so we had the pregame basement, which is kind of, we don't really know what happened there. Then had the sea come in, sea go out, sea come in, sea go out. Then we had the mountains coming up on the west, on the east, and shedding rock for hundreds of millions of years, or not hundreds, tens of millions of years, shedding rock to the west, and what created these rock units. So then we go younger rock. So if I don't know if you remember or not, but this is about the top of the Grand Canyon. So we don't see that. So there's younger rocks we see further north and like west areas, Zion areas have these younger ones. Colorado Plateau, the Colorado National Monument has these rocks, the younger rocks, Arches, Canyonlands, those all have these younger rocks, thing Wingate sandstone and Trotta sandstones. So during the Jurassic years, let me see if I have notes here. Again, you had major mountain building on both the west and the east. I think it was called the severe orogeny in the west, and the Uncompahgre uplift on the east, which was kind of rejuvenated several times. And also, if you look at the sandstone, these thick sandstones, the Wingate, the Navajo, and the Entrada sandstones, those are all dune sands, preserved dune sands. So this is like, if you think about Sahara in Africa, that's what the surface of the earth looked like in the Colorado Plateau area during the Jurassic and oldest Cretaceous eras. So, and then you would intersperse that with the Kayenta, the Carmel, those kind of formations, the Manco Shale, the Dakota sandstones. Those were like right at sea level. Remember, we're still at sea level, right at sea level, but like these meandering streams going across, really like think of the coastal plains of Georgia and Alabama, that kind of low level lazy rivers. All these rivers are coming off these mountains to the east and the west, bringing all that stuff down and then redistributing it out. And when it gets dry, then the wind takes over and makes these big sand dune fields. And when it's a little wetter, then you'll have more silt come down because the water can take it and the wind doesn't blow it away. So this is all kind of a time period of dune field time and shallow, very coastal area times. Then we have the middle tertiary. So after we get out of the Cenozoic era into the tertiary era, you have a couple of different things. You have a little bit of uplift around the area. This is when that Kaibai Plateau, remember that big kind of upwarp, what we call the upwarp? The Kaibai Plateau was uplifted. There's volcanism around the periphery of the Colorado Plateau, like down near Flagstaff, and the San Juan Mountains in Colorado. Those are extreme volcanic areas. Also, the entire area began to be uplifted. So we're no longer at sea level. So we're no longer having deposition as the water reaches home base back in the ocean and losing all of its energy and depositing all that material. It still has a lot of energy because it's still going down to the ocean and carrying all that material. So, but this series of pictures on the right, they're not really maps because there's no scale, but you can think about the horizontal scales, maybe 100 to 150 miles across, left to right. So this is the ancestral Colorado River 40 million years ago, or maybe 50 million years ago. And as the Kaibai Plateau uplifted, it basically diverted the Colorado, it basically just dammed it up and it diverted it to go down to the Gulf of Mexico. It used to go down to the Gulf of Mexico instead of out to the Baja California area. And then somehow, if you look at the center one on the left, Lake, and I can never say that one, Bittahoochee, Lake Bittahoochee, the outlet gets blocked. And so Lake Bittahoochee gets bigger and bigger. And eventually, if you look at the center right one, it basically flows back up the river and around and recaptures the old historic Colorado River basin, and then effectively drains that lake and establishes the current path of the Colorado River today. And where Lake Bittahoochee was is now the Little Colorado River. Little Colorado River. The Little Colorado River is the most unique tributary to the Colorado, in the whole Colorado river system, because literally the river used to go down that canyon and to the Gulf of Mexico instead of out to the Baja California. So it's really fascinating. If you ever want to read about that, I have some papers you can read that talk about that and how they figured it out. Was pretty fascinating. It was it had to do with, again, paleontology. They were looking at these specific little microfossils that they knew occurred in the upper system. And then for a while, they couldn't find them in the lower system. And then after a while, they found younger paleofossils, which occurred along the whole system. They couldn't figure out why that was. And this is why, because for a while there, those paleofossils or microfossils that were in the upper system actually went out to the Gulf of Mexico instead of down to the Pacific Ocean. Pretty amazing, and amazing sleuthing by the geologists who figured that out with some really, really subtle information. So, and then let's go to Minty.com again, and it's going to be a new code. Let me show you what that is. And I'm going to do screen sharing. Oops, go back. I'm going to do this guy, and here we go, this one. I can't see it because the Minty thing is going. Okay, so go to minty.com. You may have to go out and come back in, but the new code is 562931.5, and you can vote. I'm going to do that myself. So go. Yeah, you have to basically delete it out and go back. Minty.com. And then the code is 562931.5. Submit. Go. Perfect. Yeah. I know nothing. I just told you. Yeah. So the river used to go basically up the little Colorado out to the Pacific or to the Atlantic Ocean instead of down to the Pacific. Pretty cool stuff. All right. We're going to go back to geology here. Share and play. There we go. Okay. So, and then the last period is today, right? Modern times. So the Colorado River, I mean, the whole Colorado Plateau was uplifted in our last the period we talked about, and it was uplifted quite a bit, probably between 10,000 feet and 15 or 20,000 feet, and just overall. But remarkably, there's very little faulting. It basically kind of uplifted as a big gigantic unit, and it's the size of, you know, Norway that was uplifted with relatively little deformation of the rock over time. And so nowadays, so once you uplift it, then your water that falls in the form of snow and turns into meltwater or rain or whatever, or wind, has a lot more energy and basically starts eroding away. So that's what we are today. The last period, what we are knowing about it is erosion. So that's erosion caused the Grand Canyon, erosion caused the Desolation Canyon, Labyrinth Canyon, Yampa Canyon. All these canyons were formed in the last 20 or so million years. And if you look at remember the morphology of the river system, how the braided stream has a high energy and the meandering stream has low energy. Well, you wouldn't expect to have a meandering stream to be entrenched into a deep canyon like that, because typically when you're eroding that much, it's going to be a high energy stream. But basically, as the rock was uplifted, these meandering streams kind of got stuck in their meanders. And so that's why that's kind of a bit of a, I don't know what the right word is. They don't fit. The meandering stream doesn't fit in a deep canyon as far as what you would think of as normal geomorphology techniques or happenstance. So go to the next slide here. So why do our rivers look so similar? So across most of the Colorado Plateau, we have a similar environment and ecosystem, a high desert with scattered areas of forest, which is underlain by that thick stack of stratified rock, which is basically hardly deformed at all, and it has remarkably beautiful colors along the strata. And then, like I said, relatively little structural geology, so hardly any faulting, hardly any folding. But most of all, you have large rivers that have basically eroded out these fantastic canyons in this remarkably stable part of the crust, and it makes for a unique physiographic province, and explains kind of why we see similar style of rocks and cliffs and you know, slope formers from everywhere from the bottom of the Grand Canyon up to the Yampa River Valley. And then we have another question with Minty. One more question. Ooh, I'm gonna try to do it this way. Here we go. Share. Is this it? I think so. And we'll go to the next slide. Here we go. And so the same code. what factors make the Colorado Plateau characteristic and remarkable? And you can pick as many or as few as you like. Oh, it only lets me pick one. Oh, that's too bad. It's supposed to be able to pick more than one. Oh, well. Well, pick the one you like the most. I think you can do it more than once too, so. Oh, okay, only let you do one. All right, well, it should be everything but dinosaurs made the canyons with their little hands. So, yeah. So that one I didn't set up right, so my apologies on that. Cool. All right, go back to our, where did my thing go? I'll just go back to here. Desktop. There we go. Oops. There. Oh. Okay, well, here's our little treat.
Grand Canyon Customer Service. This is Porter Edmondson speaking. How may I help you?
Hi, yes,
Hello.
yeah, quick question. Do you know Grand Canyon rocks? Yep. Kaibab, Torah, Weave, Coconino, Hermit Shale, Supai, Red Wall, Temple Mob, Bright Angel Shale, Tub Beats getting steep, going down to Inagor, Super. I'm Super Grouper!
Grand Canyon.
Get low. I'm the shist. Nice.
It's a shit.
The Grand Canyon.
I'm the shit. Kaibab, Torah, Weave, Coconino, Hermit Shale, Supai, Red Wall, Temple Mob, Bright Angel Shale, Tub Beats getting steep, going down to Inagor, Super. I'm the Super Grouper. Ram, get low. I'm the shist.
Kaibab, Toro Weep, Coconino, Kaibab, Toro Weep, Coconino.
Kaibab, Torah, Weave, Coconino, Hermit Shale, Supai, Red Wall, Temple Mob, Bright Angel Shale, Tub Beats getting steep, going down to Inagor, Super. Grand Canyon. Well, some might call me a hermit, but there's something about the Supai that really paints my walls red. I'ma build me a temple and set it up high atop a mob. A limestone bed, bright angel shale, bright enough for a trail we call foolish, a trail we call Plateau. As I walk on the Plateau, I feel so alone. Well, that's at least until I reach to Pete Sandstone. Geology, no. Kaibab, Torah, Weave, Coconino, Hermit Shale, Supai, Red Wall, Temple Mob, Bright Angel Shale, Tub Beats getting steep, going down to Inagor, Super. Grand Canyon. Okay, so if there's limestone up here, that means the ocean was here. But dude, how did this all go down? Dude's right. Deposition, uplift, downcut, erosion. Deposition, uplift, downcut, erosion. Deposition, uplift, downcut, erosion. Look, it's just a theory. All right, don't take it too serious.
All right, I'm gonna leave it there. You can watch the rest of it on YouTube if you prefer. So, and I'm gonna go to, this is our last slide, I believe. Yeah. Last slide. I'm gonna go to the last Menti, and basically that's just if you would be so kind as to leave some feedback about the talk. It's this one. So it's a new code to go back to menti.com and use the different code, and you can put comments about both the presentation and the Menti and see how you liked it. And that's all I've got. And I'll take questions at you guys' convenience. And I'm not going to show this because that's kind of for me to learn about my presentation. So I'm going to stop sharing my screen. There we go. Cool. Yay.
Really good, Lynn. Thanks a lot. I like that
I know, that's fun.
video.
Debbie and I were singing that as we were going down the river. Right, Debbie?
I was singing it tonight.
I was too. Kai Dr. Coconino Hornshell. It's fun to remember the units. Helps you remember the units. So, but yeah, fun.
Yeah.
Excellent.
Yeah, let's see. you have any questions? Oh, GA means a million or billion years instead of MA, million years, is billion years. I was dancing. Yeah. So cool. Does anybody have any questions that I can answer? Some of these I can't answer, but basically the moral of the story is the whole area was right at sea level until about 40 million years ago, and then it started being uplifted and eroded. So yeah, pretty cool. It's amazing. Beautiful area.
Better to go up than to go down. I appreciated learning that it's the iron that makes the rock red, because I love the red rocks.
Yep. It doesn't take very much. It's really a little bit. And actually, some people theorize, and I don't know I haven't heard lately what the rule was, but if oil has gone through those sandstones, which are very porous, sometimes it'll absorb the iron and leave it white. So you'll have the same rock be red in one area and white in the next area, like a mile away. And they think it's because the oil went through that rock and kind of stripped all the iron out. But I don't know if that's been proven or not. That's one theory.
Hey, I think I don't know whether you've told me this before or somebody else has told me before, but you know, like how something like the red rocks, there'll be like streaks that looks like oil.
Oh yeah.
What is that? What is that? Is that
called desert varnish? And there's a guy out of, I think, Flagstaff, the Northern Arizona University, who studied that for his entire career and still doesn't really know, but they think it's a combination of like algae or fungus on the surface, that the dirt will stick to that algae or fungus over time, but it has a really rough life. It hardly ever gets any water, but you'll notice it's darker where the water comes down. And so the idea is that algae or fungus or whatever that little single-celled organism probably is lives there, and then if it gets wet, maybe the dirt that blows on sticks on. But this guy out of Northern Arizona University has been studying this for years, and he has done scrapings from all over the world, and they're remarkably varied, but they look remarkably the same. So it's they don't seem to have any kind of common characteristic, I think, is what he came up with. But yeah.
Cool. Thanks.
Mm-hmm.
Well, if anyone doesn't have any more questions, we can.
Yeah. Well, that song, I'll apologize in advance. That song will probably be stuck in your head till midnight.
Thanks for all your hard work on this, Lynn.
Yeah, thanks a lot, Lynn.
Oh yeah, it was fun. It was fun, and it's I like to. People usually ask me what's going on, and usually I can't answer because I haven't looked it up. So I looked it up.
Nice.
So yeah.
We'll give Lynn a big round of applause.
Yay.
Cool.
Awesome.
Keeps getting better.
Yep.
Yeah. All right. I'll talk to everybody later. Have a great evening.
Good
All
night.
right.
Good
Good
night.
night.
Bye.
It was nice meeting all you people.
Bye,
You too. Bye, Sheila.
Bye.
Bye, Lynn Marie.
Bye, Sheila.